All right, that's good enough. Okay, so let's do this class here. It's shorter than the previous one. I'm going to talk now finally about independence. Yeah. So once you have your probability space, omega A and mu, we have events in there. We can talk about events being independent. Okay, so this means we don't even need this to express that. The probability of A intersect B, you know, that's the measure mu of A intersect B. Yeah, but people check on how many. So okay, this is the probability of A times the probability of B. Whenever that happens, we call them independent, these events. Okay, so why is that? It's probably because, well, you have your omega here, and here's your A, and here's your B. So if you know that you are in B, let's say, what information does that give you about the probability of being in A? Well, the probability of being in A is given by the size of the intersection divided with all the numbers in B, right? The size of B. So probability of A, given that you know that you're in B, the probability of A intersect B divided by B of B. If I'm not wrong, they call it like base law or something, but it's really obvious, right? And now, if you have this, you see you stick that into the numerator up there, and the P of B cancels out into the P of A. Basically, knowing that you're in B gives absolutely no valuable information whatsoever about whether you're in B or not. Okay? So that's independent for you. Now, two random variables can be independent. And we saw that last class, right? With it's back. We can feel it like, okay, if I know that I have a certain value of one variable, does that help me to guess what's the value of the other variable if they are independent? Not at all. So this boils down to this thinking here that for x1 it's independent of x2 if the pre-images of all measurable sets here, A, and usually this, of course, is something like a Grell sigma algebra or even natural numbers, finite sets. But of course, in the generality of the book, this can be anything in one sigma algebra, whatever the x is studying. But anyway, if x1, the pre-images on the x1 and the pre-images on the x2 of other sets D, if these are independent for all A and B. In whatever they are, A and B. Yeah. Okay. This is the independence of random variables. But the book goes further. Now we introduce the sigma algebra generated by x1. You can guess what that is. So it's the sigma algebra generated by the pre-images of all sets A, where, well, let's say that we're dealing with the random variable with values in the real, so then we can take the models. Yeah, otherwise, sigma. Okay. So all possible measurables. So the smallest sigma algebra that contain all the sets making x1 a measurable function. Now it's more or less obvious that, okay, and then we call two sigma algebras independent. If the sets from one sigma algebra is always independent, this definition here, set from the other sigma algebra. And with that definition, it's pretty obvious that two random variables are independent with this definition if and only corresponding sigma algebras are independent. Okay? So two sigma algebras, sigma 1 and sigma 2, or maybe I can call it A1, A2 are independent if A is independent of B for all A in A1 and B in A2. Okay, segue path here, right? So, but it gets interesting very quickly because now, so to me, like, why would you just make things more complicated? These are independent. You don't need this extra layer here, right? But watch out, it's soon going to get very interesting. First of all, let's take an example. Okay. So it's a bit nice because this is the first time we're having sigma algebras which are different than these just Borel and debate that we never had any non-trivial examples. Let's do like we had in the previous lecture. This is my y1, this is my y2, and my omega here is the interval from 0 to 1. What is then the sigma algebra generated by y1? Well, it consists of 4 steps, right? So you have, you could say it was right continuous, yeah. So you have the interval 0 to 1/2 open end, interval 1/2 to 1, well, okay. That's very open end here for the symmetry of things. And then you have the empty set, and you have the omega. So we have the 4 point set. Yeah, okay. Sigma of y2 would similarly be, but now it's a bit more complicated, but we get again 4 sets, right? So we have basically the level set here, the level set there, full space, the void space, and those sigma algebras, as we saw in last class, they are independent of each other. So it's satisfied. The same here with the Lebesgue measure as a probability measure. Okay, nice. So, why have the idea of independent sigma algebra? Because we're soon gonna see examples of sigma algebras that are not connected to any random variable whatsoever, but still, okay. So first, let's do this proposition 10, 1, 7. Don't obscure one, so when you read it, you don't understand what it says. When you finally understand what it says, you get annoyed because it doesn't, well, but you don't see that it has a great potential, but then it's being used over and over again. So basically it's saying, I'm going to simplify it, that there is a sequence of independent random variables. And now I split this up into 2 parts. Okay, I do the sigma algebra generated by, let's say, the odd ones. And then the sigma algebra generated by the even ones. Now, if these are all independent, then this sigma algebra and this sigma algebra is again going to be independent. So the statement, you can try to read it, is much more general. I don't think it just starts with random variables. If you have a bunch of independent sigma algebras, not even countable, so enumerated by some index set, you split that index set up in disjoint pieces, and you do the sigma algebra generated by one bunch of indices, and sigma algebra generated by another bunch of indices. Then you get 2 bigger sigma algebras that now are independent. Yeah. But the key point is this sigma, whatever, yeah, wherever you throw into the construction, this sigma algebra do not have anything in common with what you throw into that one. All right? Okay. What can we do with such a statement? Well, actually, a lot. So already, let's do an example here. So let's say I want to compute something concrete. There are 3 random variables. Okay, I know nothing about them. The only thing I know is that the expectation of each one is equal to 0. And now I want to compute, okay, let's make it a bit complicated so that A be the set of all omega such that max x1 of omega, x2 of omega is bigger than something, let's say 1 to equal 3. So now I have some set here. And now we're going to integrate x1 plus x2 times x3 with u over this set A here. All right, so what's the answer? Think about it. Both of you think if you know the answer. Something very similar to this comes up in the computation in the proof of the book. And the first time I saw it, I was like, I didn't follow. So to me, like if you live on the left-hand side of things in what I call it, in the probability world that you really want to compute this one, I don't know how to do that. I wouldn't do. Okay, so here's how we do it. Going over to the right-hand side again, and using this thing here. So, introduce, so I'm going to call this star for now. Now I introduce a new random variable y, which is the characteristic function of A, and x1 plus x2. Okay. No. Yes. x1. Now we're okay. So clearly, x1 is measurable in this sigma algebra because it's a smaller sigma algebra where x1 and x2 are measurable. So then I can sum up two measurable functions to get a new measurable function. So x1 plus x2 is in here. These sets, if we now go back to chapter 2.1, I think, sets like this. Is again, if these two are measurable, well, in this sigma algebra now, with for this example, the one I sent up there, it could be a finite dimensional sigma algebra. It could contain 8 sets. Or even less. 6 maybe with that example. 47, 47. But okay, so anyway, so this set A is open this sigma algebra. If I multiply with the characteristic function of such, it's still fine. I can do that. But all together, this is measurable function in there. Okay. Now, to get along here with my star, I'm integrating now random variable y times random variable x3 in my new space, but then we swap to the right-hand side. So let me do this push forward measure. Now I have an integral of y times x3 independent variables now. And I have this product measure, right? Okay. But now, so this guy is measurable here, which is independent from the sigma algebra generated by x3 to the right side number. Okay, so these two are independent from each other. And when that happens, there's another theory in the book, but I have been saying it the other way. If you have two probability measures and you want to create a random variable which are independent, you can take the product measure. Here it goes the other way. If they are independent, this guy becomes the product measure a la chapter 5 of the one-dimensional measure connected with y and the one-dimensional measure connected with x3. So this is.
So the theory I'm talking here about is 1019. Very useful. Go check it out.
You find it in 10.1 somewhere. I put up the number of. Now I have is okay, but then also I have convenience theory, which tells me that I can evaluate this as an iterated integral. Now I get the integral y dt y. So the integral x3, the dx3, okay? And this is the expectation. Well, both of them is expectations. I get the expectation of y, which I know So idea what it is, times expectation of x3, which is 0. So no idea what it is times 0 is always 0. Yeah? So this proposition here came into this step here. Yeah? Provider? Dug in, I managed to resolve this integral. Pretty fascinating if you ask me. Well, you can think what you want, but okay, this was the first application of 1017. Of course, this, well, this example, this is how we generated independent random variables in the previous lecture. Also, remember we did these functions with x1 and x2 that were independent and had a uniform distribution. So that's exactly the same algebra we were interested in then. So 1017 elements there as well. Where else can it help us? It can help us to prove the very fascinating statement known as the Kolmogorov zero-one law. By the way, a word on the proof of 1017, it bounces back to the thinking level, which is heavy stuff, right? So it's short, but it doesn't mean it's simple. So somebody thought a lot to make something so complex into such a short statement. Just because it's short doesn't mean it's not deep. Okay. Well, here's another deep statement. This is mind-blowing. So basically the statement says, informally, it says that statements, okay, what do we have? We start with x1, x2, what. We have infinite sequence of random variables. No, I don't have the book and I don't remember if they need to be independent. Yeah, probably right. But let's say independent. Yes, it has to be independent. Okay, that's the whole thing. Okay. So there are independent random variables. And then statement slide. The limit as k goes to infinity of x, k, omega exists. Okay, so for each omega, now we really need this, that okay, we have some omega here with all this infinitely many xk shooting out of it, even if this is just actually in reality the line between 0 and 1. Okay, so each omega in here gives rise to an infinite sequence of numbers. Yeah, it's a sequence of numbers. In limit can exist, or it cannot exist. So either it does or it doesn't. So we get some subset here. Now the statement is that either that's true with probability 1, or it's true with probability 0. You have no other alternative. Statement. How on earth would you go on about proving something like that? Okay, let me give you the idea. Let A be the set where limit exists. This limit up there. All right. Now this set A really the sigma algebra generated by xn plus 1 up to infinity for any n, right? Because if the limit exists, doesn't matter what happens in the first n value of the sequence, right? The limit is just something that term in course, and it can go as much up and down as it wants to, as long as the limit exists. It only depends on what happens here for any n, right? Okay, so now this means that A is a member of the tail sigma algebra, it's called tau, which is the infinite intersection of all of these guys. Right? Well, so tail sigma algebra is then independent from the sigma algebra generated by x1 dot 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 up to xn minus 1. Yes, because the tail sigma algebra, so this sigma algebra is disjoint, so it's independent of this sigma algebra. The tail sigma algebra is a subset of this sigma algebra. This one and this one are independent. Now we can use 10(1)(6) again, and this is the first time we use it with a sigma algebra that's not related to any random variable, right? So he's independent from this guy for every n. But then tau is independent from the sigma algebra generated by this guy for all n. And what is that? Well, it's the sigma algebra where they are all measurable, these random variables. And clearly, so I mean, tau by construction is a subset here. So it's both a subset of this sigma algebra and independent from it at the same time. I think actually the Kolmogorov 0(1) law, it says something like that, anyway, I'm not going to make a fool out of myself by repeating something I remember incorrectly. But to get back to our statement here, so now A is in this sigma algebra and A is also in tau. Okay? So then, what's the measure? U of A. Well, it's the measure of A intersected with itself. But now we think of this as a member of the tail sigma algebra, and this as a member of the full sigma algebra, since they are independent. I have this. Right, so now I'm looking for a number which is equal to its own square, but there's just two such numbers, 0 and 1. This requires some digestion for really understanding. I cannot say I fully understood it yet what the hell is going on here. But I mean, it's beautiful. Yes? That's something more. Or maybe just a small example, just to flesh out the lecture a bit. We can turn it off now. But there was another thing I was thinking about. If this lecture is about independence, let's have some really schoolbook examples of what it means to be not independent. So if you throw a dice, yeah, and the dice is even, you have 1/6 on the time, yeah. That's 1, 2, 3, 4, 5, 6. So this is the probability of the outcome of the dice. Now, if you roll 2 dices, you can register the probabilities in a matrix. Okay, so this is first die, second die, and what's the probability? We know if these are independent, it is a pair pair die, so the second row doesn't depend. Well, pair means okay, so the probability is equal, and then it's independent, so it means the second row doesn't have any influence. For the first row, it's not any influence on the second row. So then what we get, we have to multiply these probabilities, we get 1 divided by 36, yeah, like this. So, what would be an example of a fair die, but which is not independent? That's very easy to construct. Let's just write here 1 divided by 36, and then 0 divided by 36, then 2 divided by 36, and then 1 and 1 again divided by 36 divided by 36. And we can flesh out this, right? But the point is, if I sum up these numbers here, I get 1 divided by 6. So if these numbers sum up to 1 over 6, and these numbers sum up to 1 over 6. So the point is, if I know the outcome of the first die, then I know that I'm in this column, and now it's no longer fair. The probability of hitting 3 is 0. Yeah. So yeah, an example that you have 2 fair clusters of a die without them being independent. Now let's make it more interesting. Can we have a sequence of random variables so that any pair of 2 is independent, but they are not independent? And I will give you a nice example of that, an easy example of the fact that this is true or false. I mean, so you can make them that any pair of 2 are independent, but they are not independent altogether. So let's do coin flips. Yeah. So outcome of the first coin flip is 0 or 1. Outcome of second coin flip is 0 or 1. And outcome of third coin flip. Now put that on an axis here. Now basically we need to come out with 8 numbers, giving me the different probabilities here. There. Right? So I have a sort of cube here of probabilities. Very hard to make it. So normally you would have, if this is pair and independent, you would have 1 divided by 8 in every index here. So how can we rig it so that this is not the case? Well, let me put a quarter here, 0, 0, quarter here. Now I flip that with 0 there, a quarter in this corner, 0 here, and a quarter in this corner. You get the idea. So what's the probability matrix of just, okay, so this is the x1, x2, and this guy is x3 variable. So the probability matrix of just x, if I don't know anything about what happened in x3, I have to sum up, right? So I project this lower level onto the upper one, so I sum up, yeah, in this direction. So what do I get then? Well, I get a matrix 1 quarter, 1 quarter, 1 quarter, 1 quarter. Okay, so this is independent of each other. If I know something about x2, it doesn't tell me anything about x1 and vice versa.
So I realize here again that I'm using, independence is a condition on level sets, right, of the random variables. But what I'm using here is implicitly 10, 1, 9 again, which says that 2 random variables or a bunch of random variables are independent if and only if their probability measure are product measure of the respective probability measures from the smaller dimensional space, right? So this is what I'm checking. I'm just looking at this matrix. This is like I'm saying, oh, it's a product measure here, and therefore they're independent. So it didn't occur to me before that that's actually not the definition, but okay. So it's a valid way of checking it because 10, 1, 9 goes both ways.
And then if you this cube, if you start to look at it from different angles, you realize the same thing happens everywhere. But any two of them will always be independent, but they are clearly not independent, yeah? So this, what does this say? So a quarter here means that I can have with a quarter probability the sequence 0, 0, 0, that's okay. And with a quarter probability, I can have the sequence, so what's the first one's is 1. What the point here means, the third one is 1 person, okay. So this point here corresponds to first one is 1, third one is 1, but the middle one is 0. So that's an allowed point. This is the 1, 1, 1 point. Here I have first one is 1, second one is 1. I have 1, 1, 0 as an alternative. And we'll put this guy now. So it is 0, 1, 1. So with a quarter probability, these strings come out. So you see here, if I block this one, I have a quarter probability of 0, 0, 1, 0, 1, 1, 0, 1. So block this one, a quarter probability of each of these combinations. Yeah, nice. All right, that's what I have to say about independence. Yes, so with this, you can read up until the Kolmogorov 0-1 law in 10.2 somewhere, I think. Next time we're doing convergence of random variables, law of large numbers, and that will be the end of the crash course. Thank you for watching.